Okay, so welcome everyone to a new EDT community talk. So we are resuming after a summer break. Today we have Randy Paredis as our speaker, and we have two more talks before the winter break. On the 10th of November, we have Jean-Sébastien Sautet with the title Harmonizing the Complex Evolving Digital Twins to Bridge Data, Domains, and Decisions. This talk will give us lessons from their digital twin journey, integrating disciplines, people, and data for decision systems. And on the 8th of December, we have Edward Camburjan. As a final talk before the winter break. So about today's speaker, Randy is an entrepreneur at TMC Europe, currently consulting at Atlas Copco. He obtained his PhD in March 2025 from University of Antwerp, where he specialized in digital twins. He explored the generic architecture and framework for model-based design of digital twins, and he also has interest in discrete event system specification as a common denominator for discrete event modeling languages. In this talk, he will introduce the twinning paradigm, a unifying concept that brings structure and clarity to the diverse systems. The talk will also explore how design choices across different stages shape the behavior and performance of these systems. So thank you very much for being willing to give us a presentation today, and the floor is yours, Randy.
Yes, thank you, Leonard, for that lovely introduction. Let's see if I can share my screen. Okay, it should have worked. Yeah, thanks for that introduction, and thank you to the EDT community for inviting me to give this presentation about this topic that I personally find very interesting and pertinent in our research area, and that is the foundation for a twinning paradigm. As Leonard introduced in my introduction, if my slides move, yes. As Leonard introduced, I indeed got my PhD a few months back, and that was on a multi-paradigm modeling foundation for twinning within the context of systems engineering. And today I wanted to do a little bit of a deep dive into this topic in order to pinpoint and highlight some of the important research aspects that I found, and some of well, basically, I want to open up the floor to start new discussions and new research avenues to be explored. I do have to start with a small caveat, and that is that maybe to those of you who have been here in the EDT community for a while, some of what I might be talking about will sound a little bit familiar, and that is because well, my supervisor, Hans van Geelwe, gave a talk almost 3 years ago now about my current research, well, our current research at that point in time. So today I will try to be a little bit of an addendum to that, and also provide a little bit of an updated version and an updated vision for what he talked about. But if you are interested in this topic, I also recommend to go watch his talk afterwards. And let's start with, well, digital twins, as we all know and hopefully love. What is a digital twin? That question is very difficult to answer because, well, here on the slides, there's 9 different definitions for a digital twin. There's this literature study from Dalibor et al. That lists, well, it states there are over 100 different definitions. I believe that study is from 2023 or maybe even earlier. So in the meantime, a lot of additional definitions have been introduced. And some of these definitions are incredibly broad. Some of them are very narrow and focusing on a very specific use case or domain or context. Some of these definitions even up to a certain level contradict each other. So this question of what is a digital twin is actually very muddied. But where everything boils down to is, in fact, this overview. This is a slide from Michael Greaves showing the conceptual ideal for product lifecycle modeling, where they introduced the idea of a real space or a system under study that communicates with this virtual space or an abstraction or a model with respect to a very specific view or property of interest. I'm personally from the modeling domain, so to me this makes most sense as a model, but there is indeed research in which this virtual space is, well, can also be seen as something else, but let's call this a model for the purposes of this presentation. And we have within the setup, we have a system under study that sends data, environmental data, sensor data, and so on to the model. And the model can then use that in order to produce some results, or some additional process can be executed onto the model like a simulator. And based on that, we are able to obtain some additional information or some processes that the system under study needs to execute. Also very interesting in this slide already is the fact that the virtual space actually has multiple instances that can exist at the same time, multiple virtual spaces that can coexist, because that's indeed very realistic, because maybe some model is very good for a very specific purpose, but another model is also very good for another very specific purpose. And if you want to have both, well, you need to have both in order to get that information out of it. Now, because this area of digital twin and all related terminology is muddied, I'm going to stick to a very specific naming convention throughout this presentation, and I'm going to be calling this system under study in its environment. I'm going to be calling that the actual object. And I'm going to be calling this model or this abstraction in its environment, I'm going to be calling that the twin object. Let's have a look at an example. And there's a proof of concept that I created throughout my PhD. This is a very simple line following robot. More specifically, it's a non-holonomically wheeled differential drive line following robot. What that means, it's a Lego robot that drives around using normal wheels. And these wheels can be steered independently using servo motors. And that allows the robot to drive around all throughout space. And the main purpose of this robot is to have, is to follow a line as accurately as possible. For instance, here on the left, I don't know, maybe this highlights it better. Here on the left, this is a section of a line. I have this abstraction of a sensor drawn on top of it, or what the sensor sees, and maybe it says it's 70% black, so we might be able to conclude that the robot is on top of the line. Maybe if it drops below 70%, it's not on the line anymore, and we need to find the line again. That's the very simple setup, and I realized that using Legos, and in my living room with this entire setup with this ground plan, I used a white line on a dark background instead of a black line because, well, I had this black background available to me. And well, on top of that, I placed this camera in order to objectively determine the position of the robot. And that's what you can see here. This is a dashboard that basically shows what the robot is doing. And you can see here this brownish orangey box. That's actually a cardboard box that I placed on top of the robot, such that the object recognition software was minimal in this context, because the contrast is higher and so on. So I built this robot, and at the same time, I also created a model for this robot. Because I know it's a differential drive robot, I'm able to construct these formulas. This is a very simplified version of these formulas. You can go in much more detail, but I'll spare you about that information. And these are ordinary differential equations that you can then turn into causal block diagrams, some sort of Simulink-like models that you can then simulate in order to mimic the kinematic behavior of this robot based on the value from the sensor that it obtains. And that's actually also partially visualized here in this dashboard. You can see here on top, there is this stack of arrows. And the bottom arrow may be barely visible. If you can't see it, believe me that it's there. There is this dark blue arrow that indicates the position and heading of the robot as determined by this camera and by this object recognition. On top of that, there is this, well, there's this orange arrow that you can ignore, but on top of that, there is this red arrow that indicates the position and heading of the simulation of these kinematic formulas when simulated. And then you can run a lot of different experiments. Here is one of these experiments with robots driving around again, and I have plots the position that I have determined both from the simulation and from the real robot, and you can see both follow the same trajectory very well. But after a while, they start to deviate a lot. And this is where we might be interested in introducing anomaly detection and fault analysis in order to identify what is exactly going wrong and maybe fine-tuning this situation again. But for the sake of this proof of concept, I have not gone into that level of detail. Let's have a look at another example. And this is maybe a more exotic example. This is the story of the Apollo 13. To people who are not familiar with this story and want to know more, it's actually pictured very well in the Apollo 13 movie starring Tom Hanks. But basically, what is the story? It's that this space capsule, this Apollo 13, was up in space. Something went wrong. It was spinning out of control. The astronauts were losing oxygen, and they did not know what to do or what was happening. So NASA took all of the information from the space capsule that was up in space. They put it inside of these machines. These are training simulators for astronauts in order to get familiar with the situation of such a space capsule. So NASA put the current behavior of the Apollo inside of these training simulators. They called back in the backup crew and told them to figure out how to get the astronauts home back safely. And as you can see, this mimics this figure from Greaves as well. We have got our actual object, which is our space capsule that was up in space. We've got our twin object, which are these training simulators. And there is this feedback loop because NASA obtains information from the real capsule and it feeds and based on the results from the training simulator, this feeds back into what's happening. Well, what the astronauts should do in order to get home safely. To a lot of researchers, and including NASA actually, this is actually the very first digital twin. However, I disagree. My main concern with this approach, while it perfectly follows the structure, is that I fail to see the digital part of it. There is an electromechanical entity, the space capsule, and another electromechanical entity, the training capsule, and they are mimicking each other based on the data being obtained and the orders being sent back. So they are indeed a twinning system, and inside there are also social entities, you can say, these astronauts moving about, but I fail to see the digital part. I will agree there are likely screens and buttons and the communication might happen digitally and so on, but that's usually not understood as the digital twin part of this setup. So even though this is called a digital twin, I would not use that wording. Let's have a look at another example. Completely different domain, much more recent actually. This is an article from Porsche. And Porsche said great news, we built a brand new car and it's a hydrogen car. And even better news, this car does very well on the Nordschleife, so on the Nürburgring. To the people who do not know the Nürburgring, it's this testing track on which most consumer-bought cars are tested in order to get somewhat a global ranking in how well certain cars do. So if they have a hydrogen car that does really well, that's actually a very good positive for the automotive industry. However, halfway the article, they said, Porsche Engineering tested it in a luxury segment reference vehicle, albeit entirely virtually. The drive was carried out using what is known as a digital twin. So here, Porsche uses digital twin actually to mean, well, modeling and simulation. It's purely that. We do have this twin object that exists, but this actual object exists somewhere in someone's mind, or maybe in some hidden facility they are actually building it. But we can assume for the time being that this is only a conceptual actual object. So our twin object, our simulation, might influence how Porsche will actually build this actual car. And based on what they want to do to the car, or how they want it to look, or what they want to add, they might ask the simulation, okay, if we add this, what are the results? Is this good? And this gives us this iterative design approach that in this context is considered a digital twin, even though this actual object does not really exist yet, but will exist at some point in the future. And this setup, if you look at the literature, this is also commonly considered within the scope of digital twins. So I'm not saying that this definition is wrong. By the way, for the Apollo, I'm also not saying that understanding that wording of calling that a digital twin is wrong. I'm just saying that I do not agree. Here, I would use more modeling and simulation instead of digital twin, but to a lot of people, this can also be a digital twin. I will look at one more example, and that is actually the my favorite example, but also the most exotic and the most imaginative. And that is the story of sand tables. Sand tables were originally known as the abax by the ancient Greek. It's the predecessor to the abacus. Why? And that's what you can see here on this figure. There's a painting that was painted on the Darius face, actually in 340 BC. And basically it shows a sand table, and it was literally a table filled with sand. And the ancient Greek used that in order to learn how to write, how to draw, how to do mathematics or geometry, or all of those things. And after a while, the military looked at it and realized, hold on, we can draw our battlefield in the sand. We can use pebbles or rocks to represent our troops. Let's place a scout on that hill that watches the battlefield, and the scout can inform us how these troops are moving about. And then based on the movement of these troops, we can look at it, we can make an informed decision in order to make orders for the generals to have our troops move potentially differently. You can clearly start to see this same picture here again within this setup. And this is a very known thing nowadays, known as a wargaming table, and it appears everywhere throughout history. Here on this picture on the top right, it's a picture from the bunker underneath London during the Second World War, where you had the head of the military watching this table, where these women were moving about these little figurines that represent planes in order to figure out what the best trajectory for all planes was, and what they should do in the war. And you can see there are multiple of these tables inside of this room. this is so well ingrained in us that it appears in video games, it appears in board games like Risk, like Catan, even Dungeons and Dragons. It's such a well-known concept. It also appears in other kinds of media. Here, this is a still frame from Pirates of the Caribbean, my favorite movie franchise of all time. And you can see, well, it's very badly pictured in the movie, but you can see there is a wargaming table where they have ships and little pawns that need to be moved around in order to potentially plot the trajectory for all these ships, or see what the best trajectory would be in this scenario or in this era of warfare. But this is a very well known and well ingrained example of a system that looks a little bit like this. And in fact, if you have a look at some of the literature, I found a paper, I've forgotten the source, but for a recent, warfare, where they use AR and VR instead of, a table with sand, they also will start to refer to it as a digital twin. So we indeed have this same structure reappearing, but if we go back to the to 340 BC, I'm not comfortable calling this a digital twin, because what is digital in that sense? It's a social entity, let's say, this battlefield that interacts with this solid entity, maybe, where there are these rocks and sands that interact with each other. So yeah, at this point in time, it's not a digital twin, but it's still a twinning system. And even here, up to a certain level, you can say, okay, this is already more digital, but I don't think the word digital exists, well, in the sense that we know it to this day, has existed for too many years at this point in time. So this still follows this exact same structure, but is still not a digital twin. So there exist other examples than just simply the digital twin that are fit in all of these boxes according to a lot of these definitions. And that brought us to this vision of, there exist so many different definitions, so many different alternatives, so many different variations of this digital twin, and everyone is using digital twin to mean something else. And a lot of people are trying to find the holy grail, the best definition to put everything under for this digital twin. And we told ourselves, maybe it doesn't make sense to start looking for this holy grail of a definition. Maybe we need to look at all of these digital twins that exist, and we need to accept that it's a spectrum, that it is an umbrella basically of a lot of different situations that actually fit the same criteria up to a certain level. And that's where we will introduce this twinning paradigm in order to cover this umbrella of examples of definitions. And we have noticed that that umbrella usually spans between anywhere that means sensing or IoT, like, for instance, well, in that case, it was not IoT, but so like the Apollo 13 and so on, that's mainly sensors and real electromechanical interactions. But it can also go to purely modeling and simulation. What is an important aspect that I should mention, that is this thing that we have taken from this famous definition from Madni and Lucero, and that is that basically says, well, we've got our twin object, we've got our actual object, and both need to be synchronized. Both need to be continually updated throughout their life cycle. Why? Well, because if you don't, they start to deviate a lot, and you cannot make a decision based on something that has been drifting apart with the thing that you're wanting to make a decision of. So it's very important that they are continually updated. But if you have these two systems, that feedback loop, in a sense that that they need to twin each other and that there is this continual update, then it technically fits this full scope of being a twinning system or falling within this category of a of the twinning paradigm, which gives us the foundation for the twinning paradigm. And I still have a little bit of time left, so I will go to showing how this foundation can fit within this broader context of systems engineering. And I did that throughout my PhD with these 5 research questions. I do not have time to go over all of them in detail, but I will highlight some of the important aspects of them. And I will especially show the first 3. And I will start with the first one. What are the most common reasons and definitions for creating digital twins or for creating twinning systems? Definitions I've shown you, and I've shown that this umbrella term of the twinning paradigm exists. But for the common reasons, I have not yet divulged that, because the main question that we are asking ourselves here is why are we building a twinning system or a digital twin? Hopefully you remember from a couple of slides back my example from the line following robot. Well, after we built it, we got in touch with a former MSDL student and currently professor at Aarhus University, Claudio Gomez, and asked them to basically look at the correspondences between our line following robot and the use case that they were using, and that is this very small incubator case study. Maybe most of you will know what this is or will have heard of it, but basically if you don't, it's this small styrofoam box in which there is a heating element and a fan to evenly distribute the heat. And what we wanted to do is to have a constant temperature, or to be able to find a certain temperature and maintain the temperature for a longer point in time. And we looked at the line following robots, we looked at the incubator, and we started to map out what the differences were, but also what the correspondences were. And that led to following larger feature trees, non-exhaustive feature trees, by the way. There's always room to add on these. This is definitely an ongoing research, and I believe it is impossible to fully map everything out because there's so much. But basically we have 3 main feature trees. First one focuses on the goals or on the purpose. Why do you want it? Do you want what if simulation? Do you want state estimation? Do you want a dashboard? All of those questions need to be asked. Then we have quality assurance. What is the quality you want to maintain? Is there any safety that you need to keep in mind? Do we need to be able to trust the system? And finally, the usage context. How is it going to be used? Is it purely for teaching? Is it for industry? Is it for training someone? Can we repeat all of our experiments? Can we replicate them? These are very important questions to ask before even starting to create your system, your twinning system. Second research question is, given that there's this vast number of digital twins, can we unify? And this question is purposefully left a little bit broad because unify can be interpreted in many different ways. The way how we looked at it is we looked at the architecture. There's a lot of examples in the literature, but there's also a lot of drawings showing the architecture for the system they've created. And we wanted to find this conceptual architecture that highlights and that involves basically all of the architectures that we were able to find, or we wanted to fit most of them into the very same figure. And that gave us this overview where you can see we've got our actual object, we have our twin objects. They are managed by some sort of experiment manager. I'll leave that for a little bit up in the air what it is, but it handles the interaction between them, and it's able to steer them and obtain information from both objects. And then there's also a user or a machine that's able to interact through this experiment manager with the actual object and the twin object. Experiment here is an important term, and I have put the definition that we have used on this slide because it's not the same definition that is commonly used in physics. But to us, an experiment is an intentional set of possibly hierarchically composed activities carried out on a specific system under study in order to accomplish a specific set of goals. In other words, if we go back to these feature trees, if we select anomaly detection, we want to do an anomaly detection experiment. If we select what-if simulation, we want to do a what-if simulation experiment. And each of these experiments has their own conceptual overview, this conceptual architecture. One thing I have not discussed on this slide yet are these red circles, and that is not only for me to identify which components are what, but also these are presence conditions. That means that in some architectures or in some examples that you find in literature, these might not be present, or these should be present. Basically, these are toggles, and everything can be enabled or disabled. And in total, that means that this figure with all of these options actually has over 8,000 different variations. But after looking at it, we believe there's only about 240 meaningful combinations and even less practically used combinations. And indeed, this fits our story of the spectrum, where we have multiple of these potential structures of this conceptual architecture. Here, without a twin object and a machine agent. Here, only without a machine agent. Here, the actual object also misses. So we can fit this in this umbrella because this also gives us this variability at this level. These are 4 fairly commonly used. If you look at the literature, for instance, this is purely sensing, where you have a user that's able to interact with an actual object. Here we have got modeling and simulation, where you have a twin object that's potentially influenced by a user. Here at the top right, this is basically the common setup for a tracking simulator or a digital shadow, according to Kritzinger's terminology. And finally, we can also have this machine agent here, and only a machine is able to influence this experiment, and a user is only to see the contents of the experiments, and so on. We can make a lot of different variations and alterations to this figure. So let's have a look at a small example where we have selected an anomaly detection experiment, which gave us this experiment's conceptual architecture. And the proof of concept that we are going to be looking at is anomaly detection in the port of Antwerp. And here you can see a satellite image of the actual port of Antwerp. And here you have a more schematic overview of the port of Antwerp. And in this example, this example, by the way, does not reflect any of the actual operation of the ports of Antwerp, but it's just to show you how you might be able to do anomaly detection. So it is very, very limited in its approach, and is by all means not a point of reference, but merely an example or a proof of concept that this can be done. What we did was we mapped out the occupancy in the port, and then also the occupancy in a simulation of the port. And at some point in time, we notice, hold on, our occupancy does not fit anymore. Our actual port is not having the same number of ships inside than according to our simulation. We get this absolute error value that exceeds this threshold, so an anomaly has occurred. We can detect that by smart coding of this experiment manager and smart being able to identify what the exact occupancy is. I will not go too much into detail on that. And then after we've done anomaly detection, let's do a fault diagnosis experiment because we want to know what went wrong. And we can do that by having multiple twin objects, multiple simulations running at the same time. Again, in reference to that original figure from Greaves, where you have multiple virtual spaces that could exist at the same time. And here, for this, for the purpose of this example, I've only done three experiments, but of course that is a way too few. It needs to be done much more and in much more detail in order to get a much better understanding. But for the sake of this example, I have just disabled this lock in the port, and I stored the occupancy, and I was able to compute this dynamic time warping score and also this Needleman-Wunsch score based on the work from Paula Munoz. And that gave me these values in order to identify how well this simulation matches up with what actually went wrong. And ideally, we want these values to be as low as possible in order to identify what the best match is. I did that with all three locks in the port. Well, all three pictured according to this slide. There are more locks, but I disabled lock A, I disabled lock B, I disabled lock C, and I was able to plot everything. And I found that in this case, lock C is the best match. But of course, this is very, very simplified and very, very fast. That I've done this and should be done in much more detail if this was an actual research and actual, actual results for the port to use. But again, this is an example. Finally, the third research question, what is the relationship between everything I've been talking about? So we've got these requirements, we have all of these reasons for creating these twins. We have all of these architectures that might be influenced by our selection for which experiment that we're going to create. How will we implement this? Which models will we use, which formalisms, or which modeling, which programming languages will be used, or which AI tools will we use in order to obtain this result? And how will we eventually deploy this? And that gives me this figure, and this is the core contribution from my research. There are 4 main stages at which variability occurs in systems engineering, and for these stages, I have applied it to this twinning paradigm. And as you can see, this first stage, it's these feature trees, it's this problem space that's been mapped out. The second stage are all of these architectures, and I've shown you this bottom figure. This top figure, I do not have time to show you, but basically that goes into detail in how multiple of these experiments might be able to be combined. And I will have a small example in a few slides. But there's a lot of additional things that we can start to discuss if we look at combining all of these twinning systems. This third stage, it's for me purely modeling and simulation, finding the right formalisms, but it's just creating the implementation for it. And again, you can have a lot of different choices and a lot of different things that you need to decide for this to make sense. And finally, you have the deployments. And again, you have this plethora of options where you need to find the best solution for your needs. And finally, yeah, these last 2 research questions I do not have time for, but these deployment choices, we might be able to find a way to quantitatively support these and to research them before it actually becomes, well, a high investment basically to find what's the best solution is. And the final research question focuses on those combinations of multiple twinning systems and how can these coexist in the same world. For that, I will end on this small proof of concept, which is Turtlebot. This is basically a Roomba vacuum without all of the vacuum capabilities, but stuffed with sensors and a smart computer. And it's able to drive around space, and it is able to map out the working area where it lives in using LiDAR technology. And we want to have a system where the robot is able to drive around, but should not constantly recompute the same path it needs to take. So what we did was we designed 3 main experiments. First one is the exploration experiment. It's basically mapping out this entire floor. Then we have got our tracking experiment, which is this dashboard, and you can click somewhere in the dashboard and the robot is able to drive to that point, and it's able to show the trajectory that it takes. And finally, we have this pathfinding experiment where, well, instead of randomly pathfinding throughout space based on I should not hit anything, we store all of the waypoints between our starting point and our ending point. And if at one point for a future trajectory, we find a subset that matches this path that we've taken, we know that path is safe and we will take that path again. And this is persistent even if the robot is disabled or is turned off for a couple of years. All of that is maintained. And this was a very fun experiment, and it basically shows how everything is able to work together and how it is important that you need to think about all of the aspects of creating a twinning system, especially if you wanted to do complicated stuff. If you're interested in my full PhD, you can find it here with this QR code or with that link. I believe I will share I will send the slides to the organizing committee, and you will have access to the slides. But in the meantime, if you have any questions, I will end on this figure, and yeah, feel free to ask any questions you have. Thank you.